Hi everyone, today we will discuss the fifth chapter of physical chemistry entitled Chemical Kinetics for the first semester, first year pharmacy students of Faculty of Pharmacy, Cairo University. The topic to be covered, the topics will be Introduction, Chemical Kinetics, the definition of chemical kinetics, reaction rates, how to measure the reaction rates, factors affecting reaction rates, half-life time for the reaction, transition state theory, effect of temperature on reaction rate, and finally, what are catalysts. If we compare the reaction of carbon with oxygen in two physical states, in graphite and diamond, according to thermodynamics, the two reactions are spontaneous. Once it started, the reaction occurs rapidly. But if we compare the kinetics of the two reactions, the second reaction of carbon, in case of diamond, with oxygen does not occur at an observable rate near room temperature. So we can use thermodynamics to tell if the reaction is product or reactant favored, but no information will be given on how fast the reaction is and how fast the reaction goes from reactants to products. However, in chemical kinetics, we can study the reaction rates and their relation to the way the reaction proceeds. In other words, chemical kinetics give us information about the reaction mechanism. To know more about reaction rate, we have to confirm that in any chemical reaction, reactant concentration decrease. At the same time, the product concentration increase. Measuring a reaction rate involves measuring the concentration of both reactants and products at different times during the reaction. Reaction rate equal change in concentration of a reactant or change in concentration of product with time. So the unit of reaction rate will be the result of division of the unit of concentration, which is mole per liter, divided by time, whose unit is second. So the final unit of the reaction rate will be mole, liter minus 1, second minus 1. Let's suggest that we have this reaction. Very simple reaction. A decomposed into B. At 0 time of the reaction, here, the container at which the reaction occurs will contain only molecules of A. After a specific time, the concentration of A will decrease, the black spheres here, and the concentration of B will increase. Going with time, the concentration of A will decrease more and more, and the concentration of B will increase. We can find this in this graph. At 0 time, the concentration of the reactant is very high and begin to decline, whereas the concentration of the product B at 0 time is 0 and begin to increase by time. So the rate is the decrease in the concentration of A by time and can be calculated as a function of B to be the rate of increase in concentration of B by time. So this slide generally discuss how to calculate the rate of any reaction according to either reactant or products. How to measure the reaction rate? For this reaction of bromine with formic acid to give bromide and hydrogen ions and carbon dioxide, at 0 time the concentration of bromine was 0.0120. After 50 seconds the concentration began to decrease. Then after 100 seconds the concentration of bromine reactant decreased more and more. We can calculate the reaction rate, the rate of this reaction, by calculating the difference in concentration between 2 points divided by the difference in time. What is the instantaneous rate? It is a change in product or reactant concentration at a moment in time. And what is the average rate? The final concentration of product minus the initial concentration of product divided by final time minus initial time. If we calculate the average rate according to the reactants, it will be the final concentration of reactant minus initial concentration of reactant divided by the difference in time, but with this negative sign. Negative sign tells us that the concentration of reactant decreased by time. What is the relation between reaction rates and the stoichiometry of the reaction? If two moles of A disappear for each mole of B to be formed, in this case the rate will be different, or a change in decrease in concentration of A divided by delta T or delta time, all of this divided by the 2, which is the number of moles of the reactant. The same rate can be calculated according to B, the product, and will be divided by 1 because the ratio of the product is 1. Generally, from this equation, if this is a general reaction, the rate according to A will be divided by A small, which is the ratio of, or the number of moles of A in the reaction, in the balanced equation of the reaction. And the rate according to B will be delta B by delta T divided by B small. the rate of C, the same thing, and the rate of D, delta D over delta T divided by D small, which is the ratio of moles of D in the reaction. This is an example of the relation between reaction rate and the stoichiometry of the reaction. Mixing 1 mole of hydrogen and 2 moles of iodine chloride at certain temperature in a closed container will go through this reaction. The rate of reaction according to hydrogen gas will be divided by 1. We will divide by 1 to gain the rate of reaction. The rate of reaction according to iodine chloride, we have to divide this ratio by 2. For iodine, we will divide by 1. For hydrogen chloride, we will divide by 2. The rate of reaction can be calculated according to either reactants or products. So we can conclude that rate of consumption of hydrogen equal half the rate of consumption of iodine chloride equal rate of production of protein equal half the rate of production of hydrogen chloride. Because the reaction rate changed with time, and because the rate is different depending on which reactant or product is being studied, we must be very specific when we describe a rate for a chemical reaction. What reactant we will choose or what product we will choose to calculate the reaction rate, and we have to have the balanced equation of the reaction to correctly calculate the reaction rate. Another problem, this is the balanced equation for ammonia when react with oxygen to give nitrogen monoxide and water. What is the rate at which oxygen reacts at the same time? What is the rate at which water is formed at the same time? If we know that at particular moment during reaction ammonia react at the rate of 0.24 mole liter minus 1 second minus 1. So you have to go back to this general slide to know how to relate between the rate of formation of products and the rate of decrease in reactants. Another example for this general reaction, for this reaction of nitrogen pentoxide giving nitrogen dioxide and oxygen. What is the rate of a change of oxygen at this time? What is the rate of a change of nitrogen pentoxide at this time? And what is the rate of reaction generally at this time? You have to correlate between the rate of reaction of nitrogen dioxide and oxygen relative to nitrogen pentoxide. Here is the formation of nitrogen dioxide. The rate of formation of nitrogen dioxide is 0.0072. we will begin now to discuss the factors affecting the rate of chemical reaction. The first factor is the nature or the physical state of the reactant. The second factor is the concentration of reactants. The third one is temperature. The fourth one is the presence of a catalyst. The first one is nature of reactant and how is this nature affecting the reaction rate. The physical state of reacting substance are very important in determining their reactivities. If we have a bottle of liquid gasoline, it can burn smoothly, but if we have the vapor of gasoline, it will burn explosively because the gasoline vapor have very high surface area, have very high spread in the atmosphere. Another example is white phosphorus ignites when exposed to oxygen in the air. On the other hand, red phosphorus, which is another physical state of phosphorus, can be kept in open container for long periods of time without any change. Another example of the nature of reactant is the powdered chalk. Calcium carbonate reacts very rapidly with dilute hydrochloric acid because the powdered chalk has very large total surface area. The same chalk, if given as a stick of chalk, not powder, it will react much more slowly with hydrogen chloride because of the very low surface area. Second effect is the effect of concentration on reaction rate. According to rate law, the rate law is an expression which shows how the rate depends on concentration of reactant. Or in other words, it is an equation that relates the rate of reaction to the concentration of reactant raised to various power. If we have this simple equation, A decomposed to B, the rate will directly proportionate to the concentration of A to the power of X. X here is called the order of reaction. So if X is 1, it's first order. If it is 2, it's second order, and 0 in 0 order. Generally, rate law says that rate equal K by concentration of reactant to the power X. K is the rate constant. It's affected by temperature. X is not the number of moles. X is called reaction order and determined experimentally. So, in general, for a reaction like this, the rate will equal rate constant K multiplied by the concentration of A to the power M multiplied by the concentration of B to the power N multiplied by the concentration of C to the power B. The rate law for the reaction, this is the rate law of the reaction. The exponent M, N, and P are the reaction orders for A reactant, A capital, B reactant, and C reactant. They are not the number of moles again. The reaction order can be 0, 1, 2, or fractions. The reaction order must be determined by experiment. The overall order of the reaction equal m plus n plus p in this case. So how to determine the reaction order, either it's 0, first or second order? We have to chase or to determine the reaction rate against the concentration of each reactant in the equation. For reactant A, suppose we have two experiments. The first experiment, the concentration of reactant A was 5 mole per liter. The second experiment, the concentration of A was 10 mole per liter. So the concentration of A in the second experiment is double the concentration of A in the first experiment. What happened to the rate? If the concentration doubled and the rate of reaction doubled, so this reaction is first order. If the concentration doubled and the rate increases 4 times, in the second case here, the concentration doubled. When the concentration doubled and we determine the rate of the reaction, we found that the reaction rate increases 4 times, so this reaction is second order reaction. For the reactant C, when the concentration doubled, the rate remains constant, so this reaction is 0 order and the reaction rate doesn't be affected by the concentration of the reactant. Here is a problem for what we said in the last slide. We have one reactant in this equation. We did four different experiments in which we had 4 different concentrations of the reactant. In experiment number 1, the concentration was 0.1 mole per liter. In experiment 2, the concentration was 0.2, double the concentration. The concentration in experiment 2 is double the concentration in experiment 1. What happened to the reaction rate from here to here? The reaction increased 4 times. So this reaction order is second order. So here the reaction rate goes up by 4 times when initial concentration doubled. Therefore, we say that this reaction is second order. If you know that now you know that this reaction is second order, and you have to determine the value of K, which is the rate constant, using experiment 3 data. Here in experiment 3, this is the concentration and this is the reaction rate. Can you determine the rate constant of this reaction? And you know now that this reaction is second order because when the concentration was doubled, the reaction rate increased 4 times. So here you can determine the value of K, rate constant. You know the reaction rate, you know the concentration, and you know that the reaction is second order. Another example, but for two reactants reaction. If you have two reactants in the same reaction and you want to detect the reaction order, you have to detect the reaction order for each reactant. So to calculate the reaction, or to know the reaction order of the reaction of nitrogen monoxide, you have to choose two experiments in which bromine concentration is constant let's to say in experiment 1 the concentration of bromine is 0.1, and in experiment number 4 the concentration of bromine is also 0.1. So here is if we compare the two experiments, the concentration of bromine will not be a factor, it's constant. What happened to the concentration of nitrogen monoxide? In experiment number 1 it's 0.1, in experiment number 4 it's 0.2. So in experiment 4 the concentration of nitrogen monoxide doubled. What happened to the rate? The rate increases 4 times. From 12 to 48 it increases 4 times. Very easy. This here we can say that this reaction or the reaction order of nitrogen monoxide is second order. You are asked to determine the rate law for the reaction and to calculate the value of the rate constant. The rate law of the reaction: rate equal rate constant multiplied by the concentration of the first reactant to the power x multiplied by the concentration of the second reactant to the power y. To know the value of x from the table, choose two experiments such that the concentration of bromine is equal and the concentration of nitrogen monoxide is different or doubled. For nitrogen monoxide we found that x equal 2, which is the reaction order of nitrogen monoxide. For bromine you will find easily that here again, if we choose two experiments where the concentration of nitrogen monoxide is constant and the concentration of bromine doubled, we will choose the experiment 1 and 2. The concentration of nitrogen monoxide is constant and the concentration of bromine doubled. What happened to the reaction rate? The reaction rate doubled, so the reaction order of bromine is first order. Again, this slide told us how to know the order of reaction. If the concentration doubled and the rate doubled, so the reaction order is first order. If the concentration doubled and the rate increases 4 times, it's second order. If the concentration doubled but the rate still the same, so it's 0 order. Here the difference between experiment 1 and 2, is that the concentration of bromine doubled and the concentration of nitrogen monoxide constant. When the concentration of bromine doubled, the reaction rate doubled, so the reaction order of bromine is first order. 1 is 1. Always the larger R in the numerator, the smaller in the denominator. To know the value of reaction constant, you will write the general reaction or general rate law, here. From this general equation you can calculate the rate constant. If you have the concentration of A and B, and you know the reaction order of A and B, and you know the rate of reaction at this specific time, you can calculate K. Here. This is another example to be done on your own. You have this reaction, this organic reaction, and you have to choose to calculate the reaction order for the first reactant. Here you can choose experiment 1 and 2. The concentration of the first reactant doubled. What happened to the reaction rate? And you have to choose another 2 experiments. The concentration of hydroxyl ions increased or doubled from 0.1 to 0.2, where the concentration of the other reactant is constant. What happened when the concentration of hydroxyl ion doubled? What happened to the reaction rate from experiment 1 to 4? What happened? And when you know the reaction order of both reactant, you can write the rate law and you can calculate the rate constant of this reaction. So now we will talk about the relation between concentration and time. What is half-life time? T-half. It is the length of time required to decrease the concentration of the reactant to half of its initial value. When T equal T-half, the concentration equal at this moment, at this specific time, the concentration of reactant equal its half initial concentration. This is a summarized table relating the order of reaction with the rate law and the concentration time equation, and how to calculate the half-life time, and what is the unit of rate constant. For zero order reaction, the rate equal rate constant, because the concentration of reactant will be raised to the power 0, which equal 1. For first order reaction, the rate will be K multiplied by the concentration of the reactant. For second order reaction, the rate will be K multiplied by the concentration of reactant to the power 2. And this is the concentration time equations. The derivation of these equations is not our issue now, so you have to know just the final equation, and also you have to know the final equation of half-life time in case of zero order reaction, half-life time in case of first order reaction, and half-life time in case of second order reaction. And very important, you have to know the unit of reaction constant in the three cases. In first order reaction, the T-half is not affected by the concentration. Why? Because in first order reaction, the reaction rate doesn't be affected by the concentration of reactant. Here we have an example, investigation of decomposition of nitrogen pentoxide at 35 degrees. Here is the reaction. The initial concentration of the reactant was 0.03 mole per liter. The rate constant was found to be 1.35 by 10 to the power minus 4 second minus 1. This unit has a meaning. When the rate constant unit is in second minus 1, this table is very important. When the rate constant unit is second minus 1, so this reaction order is 1. This reaction is first order reaction. What will be the concentration after 30 minutes? How many minutes will it take for the concentration to drop to 0.2 mole per liter? How many minutes will be take for 90% of the reactant to decompose? And what is the T-half of the reaction? This is the solution. Since units of K in second minus 1, the reaction is first order. The reaction is first order, so we can use all the equations here to calculate to write the rate law, to correlate between the concentration and time, and to calculate the half-life time. What will be the concentration of the reactant after 30 minutes, not seconds? So you have to just turn seconds into minutes. And when you know the rate constant value, you can use easily this equation to calculate the concentration or the time. In number A, you are asked to calculate the concentration of nitrogen pentoxide after 30 minutes. Knowing that the reaction constant or the rate constant is 1.35 multiplied by 10 to the power minus 4. You have K, you have time 30 minutes. You can calculate the concentration. In B, number B, you are asked to the time taken for the concentration of the reactant to drop to 0.02 mole per liter. The same equation, use this equation, to find the time will be 50 minutes. In C, you can use the same equation but with different ratios, 90% to 10%. In D, what is the T half of the reaction? Directly you can calculate it from here. 0.693 divided by rate constant. You will find that it will be 85.6 minutes. So you can calculate all these using this table, on one condition, that you know that the order of the reaction. We knew the order of the reaction in this example from the unit of K, or rate constant, and we could use this equation to calculate what we were asked to calculate. So I will slow down for you, and this is C and D. So we studied the effect of nature of the reactant on the rate of chemical reaction. We studied the effect of concentration of the reactant and rate law and reaction order. We will now study the effect of temperature and the presence of catalyst on the reaction. So in the beginning, we have to know that the rate of a chemical reaction depends on the collision between the reacting molecules. This is according to collision theory. For an effective collision, the effective means that the collision results in a chemical reaction. Molecules of both reactants have to have the proper orientation towards one another at the time of collision. In other words, molecules of both reactants must have the correct geometry. This is the first condition in collision theory. For the reaction to occur, depending on the collision between the reacting molecules, molecules of both reactants must have the proper orientation towards one another at the time of collision. The second condition, molecules must have at least a certain minimum energy necessary to rearrange outer electrons in breaking bonds and forming new bonds. This is called the activation energy. So, according to collision theory, for a reaction to occur, for an effective collision, molecules must have the proper orientation. Molecules must have the minimum energy needed to break bonds and form new bonds. This is called activation energy. The colliding molecules must have the proper orientation relative to one another and have sufficient energy to react. If colliding molecules have improper orientation and don't have enough energy and don't have the enough activation energy, they will not react, they will not give or result in formation of products. The reaction will not happen. If the two conditions of collision theory are, or one of them is not here, the reaction will not occur. This is an ineffective orientation of collision. What is the transition state theory? For a reactant A to react with B, this is a transition state between the reactants and products. What is activation energy? The activation energy here is the minimum amount of energy required to initiate the chemical reaction. It is the difference between potential energy of the reactant and potential energy of the activated complex or the transition state. If the reaction have high activation energy, this is a slow reaction. If the reaction have low activation energy, so it needs very low amount of energy to reach the transition state, it's a fast reaction. These two graphs show effectively what we said in the last slide about activation energy. What is activation energy? It is the difference in energy between the reactants in the beginning of reaction and the activated complex or transition complex here. This is the activation energy, E capital A small. When the activation energy is low, the reaction will occur fast. This is exothermic reaction, and this is endothermic reaction. The energy of the reactant is lower than the activated complex and lower than the energy of the final product. Here is what we want to know now about activation energy. If this difference between the potential of reactants and the potential of the activated complex, if this difference is very high, the reaction will take a higher time to reach the activated complex and reach the products, so this reaction will be very slow. So what is the importance of catalysts? Firstly, we have to know what are catalysts. Catalysts are substances that can be added to reacting system to increase the rate of reaction. How will the catalyst increase the rate of reaction? they will increase the reaction rate by lowering the activation energy, on one condition, that they are not consumed during the reaction. So catalysts are added to the reaction to increase the rate of reaction. How? By lowering the activation energy. And they are not consumed during the reaction. Here's the difference between uncatalyzed reaction and catalyzed reaction. In uncatalyzed reaction without any catalyst, the difference between between the energy of the reactant and energy of transition complex is higher than this one. In case we use the catalyzed reaction, the difference is lower. The difference between reactants and transition complex. From the above curve, the enthalpy change or difference in energy for the catalyzed reaction is the same as the delta H for uncatalyzed reaction. What is the delta H? Delta H is the difference between enthalpy of reactant and products. It is the same in both cases, but what is different? The difference here, difference in between reactant and transition complex, which is the activation energy. So to have faster reaction, we have to use catalyst to decrease the activation energy of the reaction, so the reaction will go faster. The catalyst lowers the activation energy, not delta H. The catalyst lowers the activation energy of the forward reaction and backward reaction by the same extent. Example of catalyzed reaction: manganese dioxide catalyzes the decomposition of hydrogen peroxide. So if I gave you a chart like this or curve like this, this is the reaction progress and this is the energy of reaction. These are the reactants, hydrogen peroxide. In this case, it's hydrogen peroxide. The black reaction is the uncatalyzed reaction. And the red reaction or red curve is for the catalyzed reaction. We can easily know that or detect that in the catalyzed reaction, activation energy is lower than the uncatalyzed reaction because of the presence of catalyst. Now we will discuss the effect of temperature on the reaction rate. The average kinetic energy of a collection of molecules is proportional to the absolute temperature. At certain temperature, a definite fraction of the reactant molecules have sufficient kinetic energy to react and to form product molecules. At higher temperature, a greater fraction of the molecules possess the necessary activation energy, and the reaction proceeds at a faster rate. This is what is given by Arrhenius equation. At certain temperature, a definite fraction of the reactant molecules have sufficient kinetic energy to react to form products. At higher temperature, A greater fraction of molecules possess the necessary activation energy and the reaction proceed at a faster rate. So Arrhenius equation gives the relation between temperature and reaction rate. Arrhenius equation in the log form is easier. This is the form we want to know. Log K, which is the rate constant, EA, which is the activation energy, R capital is the gas constant given, and temperature is the temperature in Kelvin. Log A is called the frequency factor. It's a constant characteristic for each reaction. What are the two variables in this equation, in Arrhenius equation? The two variables are temperature and K. So if you know K, you can calculate T, and if you know T, you can calculate the K or rate constant. You can write the same equation in another form. Activation energy equal (2.303) multiplied by the first temperature and second temperature divided by difference in temperature, all multiplied by log K2 over K1. Or you can write it easier in this form. From this equation, you can correlate between temperature and rate constant. If you change the temperature from T1 to T2, the rate constant will change. Knowing the activation energy of the reaction and rate constant is given. Here is an example. You are asked to calculate the energy of activation of the reaction and find K at 500 Kelvin. You have K at certain temperature, 300 Kelvin, and you have K at another temperature, T2, 400 Kelvin. What is the energy of activation of the reaction? And find K at 500 Kelvin. You will use only one equation, which is this equation. You are given K1 and K2, T1 and T2. You are asked to calculate the activation energy of the reaction. And here is the solution. You will just put numbers in the last equation to calculate this. And number B, you will correlate between T1 and T2. You have K1 and you will calculate K2, because you know in number A, you know how to calculate the activation energy. And this will be K2. Thank you.